Today we discuss the Compton effect, which gives a further confirmation of the photon model, the particle nature of the radiation. Compton scattering was discovered by Arthur Holly Compton in 1922, which is the scattering of a photon by a charged particle, which is usually an electron. So during this scattering, it is observed that there is a decrease in energy, frequency, or an increase in wavelength of the photon, which the photon may be an X-ray photon or a gamma ray photon, and this effect is called Compton effect. So the shift or a decrease in frequency or an increase in wavelength of the photon as it is scattered by an electron is called Compton effect. Okay, this was discovered by Compton in 1922, and for the explanation of the photon effect, the Compton effect based on the photon model, fetched him the Nobel Prize in 1927. So here what we have is an incident photon. A photon comes in, and here we have the electron. So this is the electron, charged particle. It is then scattered by the photon, the charged particle that is scattered by the photon, and the photon, this is the scattered photon. Okay, so this is the scattered photon, and this is the scattered electron. Okay, so the energy of the photon, incident photon, that is equal to h nu. Okay, and its momentum, that is given by h nu over c, because this is a photon is a massless particle, doesn't have rest mass. So by the relativistic equation, since rest mass is 0, we can write momentum as h nu over c, and this is the energy of the scattered photon. Its value is h nu prime, and the momentum is given by h nu prime over c, and the energy of the photon, energy of the electron, that is actually the rest mass energy m0 c square. Its initial momentum is 0 because the electron is at rest initially. After scattering, it moves with a momentum p, and the energy of this photon is now related to the momentum by this relation. So this is the situation here. An incident photon is being scattered by an electron which is at rest, and here the phi is the scattering angle for the photon, and theta, this is the scattering angle for the electron. So this is the incident direction. So phi is the scattering angle for photon, and theta is the scattering angle for electron. Okay, so we want to calculate the shift in frequency or shift in the wavelength during this scattering process. So according to quantum theory, photons behave like particles, behaves like particles, except that they have no rest mass. They have no rest mass. Like particles, it behaves, but this particle, photon, has no rest mass. Okay, so here the X-ray photon that strikes the electron, and it is scattered. The electron receives an impulse and it begins to move. Now we are using the law of conservation of energy here. In the collision, the photon loses energy and the electron gains kinetic energy. Initially, the electron is at rest. As it is being scattered by the photon, it obtains kinetic energy and it moves in this direction. Okay, so photon loses energy and electron gains kinetic energy. So loss in photon energy that is equal to the gain in energy of the kinetic energy of the electron. We are applying the energy conservation. Here h nu, that is the energy of the photon, and this one is the energy of the electron. m0 c square is rest mass energy. It is at rest, its kinetic energy 0, so this is the total energy of the electron. Here h nu prime is the energy of the scattered photon, okay, and this is energy of the scattered photon, okay, that is h nu prime, and the m0 c square plus kinetic energy. Now the electron has got kinetic energy, it is moving, so its total energy is m0 c square plus the kinetic energy. So from this I can write the kinetic energy of the scattered electron as equal to h nu minus h nu prime, okay. Now the energy, as we saw there, energy of a massless particle is related to its momentum, because rest mass energy is 0, E is equal to Pc. Here for a photon E is h nu, so P is equal to h nu over c, okay. So that is the photon momentum. Then we are applying the law of conservation of momentum here. Here we have applied the law of conservation of energy. Now we are applying the law of conservation of momentum in the x direction, okay, x direction. Here we see the momentum of the incident photon, that is h nu over c. Momentum of electron is 0. Momentum of the scattered photon in x direction, this direction is chosen as x direction, okay. So this is x direction, so this is the x direction, and here we have the y direction, okay. Here we have the y direction. So this is along the x direction, before scattering the total momentum is h nu over c plus 0, and the total momentum after scattering is h nu prime c cos phi, okay. The component of this momentum along x direction is h nu prime over c cos phi, and the component of this momentum over x direction, that is p cos theta, okay. So that is being written here. So that is written here, h nu over c plus 0, that is equal to h nu prime by c cos phi plus p cos theta, along y direction 0, because initially there is no momentum in y direction, so it is 0, and h nu prime by c sin phi minus p sin theta, okay. Here the component along this direction, that is this y direction, that is h nu prime by c sin phi, and the component in this direction of this momentum, that is p sin theta, and the initial momentum along y direction is 0, okay. So we are writing here along x direction, this is the law of conservation of momentum equation. Along y direction, this is the law of conservation of momentum equation. So from this, if I multiply this with c, okay, if I am multiplying this with the entire equation with the c, I am multiplying this with the c, okay. Here also I am multiplying with the c. Then what I get? Then I will be getting what? The Pc cos theta equal to h nu minus h nu prime cos phi, and Pc sin theta equal to h nu prime sin phi. So I am getting equation 3 and 4. These are equation 1 and 2. So these are equation 3 and 4. Now I have this PC cos theta here on the left hand side, okay, and PC sin theta here on the left hand side of equation 4. So I am squaring and adding them. So I get PC square is equal to h nu square plus h nu prime square cos square phi minus 2 h nu prime cos phi, and this is h nu prime square sin square phi. So these two combine, this cos square phi, okay, here we have cos square phi, h nu prime square cos square phi, here h nu prime square sin square phi, they two combine. So I have this equation p square c square equal to this, okay. So that is equation 5. Okay, so that is the equation 5 here. Then the third step, we calculate the total energy of electron. Okay, here we have an expression for p square c square. Now the total energy of the electron, that is given by the sum of the kinetic energy plus the rest mass energy. Okay, that we know, the sum of kinetic energy and rest mass energy, and energy is also given by this relation, the momentum, root of m0 square c raised to 4 plus p square c square. So these two are equal. So I am taking the square of this, okay, that kinetic energy plus m0 c square whole square, that is equal to m0 square c raised to 4 p square c square. And I expand this. As I expand, I will get, I am taking square of this. So m0 square c raised to 4 will get cancelled, and I will get p square c square equal to, from this, kinetic energy square plus 2 m0 c square kinetic energy. What is this kinetic energy? Kinetic energy of the electron. This is the kinetic energy of the electron. So here I am substituting for the kinetic energy of the electron. We know that is kinetic energy of the electron, that is loss of energy of the photon. So p square c square is loss of energy is h nu minus h nu prime square to m0 c square h nu minus h nu prime, and I am squaring this here. So I will get the sixth equation. Okay, p square c square equal to this. So I have this expression for p square c square. Earlier, here we had got an expression for p square c square, that is equation 5. So these two are equal. So I put them equal is equal. These two expressions are 5 and 6 are equal. So as I equate them, a few terms will cancel. This h nu prime, h nu square, that will cancel. Okay, here also I have h nu square, h nu prime square will cancel. Here also I have h nu prime square. Okay, and certain rearrangements are done here, and as I make these rearrangements, I get the equation the 2m0 c square h nu minus h nu prime. And these two get cancelled. M0 will go there, c square here, and I take this nu prime here below this nu minus nu prime. So I will get h over m0 c square 1 minus cos phi. Okay. Then if I take 1 c from here, I am taking here we have c square. Okay, here we have c square. I am taking 1 c here. So c over nu prime minus c by nu, that is equal to h by m0 c 1 minus cos phi, and this is c over nu prime, that is lambda prime. This is lambda. So lambda prime minus lambda is equal to h by m0 c 1 minus cos phi. Okay, so lambda prime minus lambda is equal to h by m0 c 1 minus cos phi. So this is the change in wavelength. Lambda is the wavelength of the incident photon. Lambda prime is the wavelength of the scattered photon, and there is a change. And phi is the scattering angle for the photon. So here we see this change in wavelength depends only on the scattering angle for the photon. So at different scattering angles, this change in wavelength will be different. This h by m0 c is the Compton wavelength, lambda c. Its value is 2.426 picometer. H we know, m0 is the mass of the electron. If the charged particle is electron, c we know, so we can calculate lambda c, h by m0 c, the Compton wavelength. And we see the change in wavelength is independent of the wavelength of the photon. It depends only on the scattering angle for the photon. It does not depend upon the wavelength or frequency of the incident photon. And the importance of the Compton effect is it constitutes a very strong evidence in support of the quantum theory of radiation, or the photon model of electromagnetic radiation. Okay, that's why in the beginning we say it gives a further confirmation of the photon model. So by explaining the different effects, black body radiation, the idea of the packets of energy, a quanta that was introduced, Einstein used that model to explain the photoelectric effect. Then its name becomes photon. So such a particle, electromagnetic radiation, can be considered as a particle. That concept, that model, that gets a further confirmation through the Compton effect. So because of this, Compton was awarded Nobel Prize in 1927. Okay, so through all these experiments or all these effects, the explanation given to it, we confirm that electromagnetic radiation has particle nature